It's a great thing to know what exponents are and to how to represent repeated multiplication quickly. But it's not so great if we can't work with those exponents once we've identified them. So what this video is designed to do, and the next several, are get you very good at exponent rules, how to do the math, the operations that involve exponents. The first one we're going to come across is called the product rule. What we do when we have common bases that are being multiplied, what we do with those exponents. So we're going to talk about the product rule right now. Now, it all stems from this idea. Imagine that you had, and you're going to discover why we need common bases, 5 to the third times 5 to the fourth. Now, they're multiplied. 5 to the third times 5 to the fourth. But wait a minute, exponents mean repeated multiplication anyway. So really, 5 to the third, well, we know that's 5 times 5 times 5. We know 5 to the fourth is 4 5s multiplied together, but I have the product between them. So essentially 5 to the third times 5 to the fourth really means 5 times 5 times 5 times 5 times 5 times 5 times 7. Oh, 1, 2, 3, 4, 5. 5 multiplied 7 times itself. So not 5 times 7, but 5 times 5 times 5, 7 times. Can you write that as an exponent? Well, yeah, that's literally repeated multiplication of the same number, of the same number. So keep that in mind. What if this were 5 to the third and this were not 5 to the fourth, like 7 to the fourth? I wouldn't be able to, I'd have 5, 5, 5, 7, 7, 7, 7. I wouldn't be able to write that as one exponent any longer. So in order for the product rule to work, you have to have the same base multiplied together. Those have to both be the same base. If not, you're seeing right here that you wouldn't be able to use the definition of an exponent to actually make exponent notation. If we do, though, 5 to the third, 5 to the fourth, they're being multiplied, hence the product rule name, that would be 5 to the seventh. Now, that's really annoying to have to do. Imagine if I had like 5 to the 31st times 5 to the fourth. I'm really not going to want to write out 31 fives and then 4 more fives. It'd be a lot quicker to follow the pattern, to see what's really going on. If you write out 3 fives and 4 fives, you have 3 here, 4 here. Together you have 7. You have that whole, oh wait, we can just add them. That's what the product rule does for you. If you have common bases and if you are multiplying, what that's doing is it's taking the concept of repeated multiplication, and continuing the multiplication. It's saying I had 3 here, I had 4 here, together I have 7. That's an addition idea. So anytime you have common bases and you are multiplying, we are going to add those exponents. Now I'm going to say something here that's going to stick with you for a real long time, hopefully. Whenever you are dealing with exponent rules, the way that you can remember basically all of them is to do this. Whatever you see, do one operational below. So exponent rules work this way. You always do one operational level below what you see. If you see exponents raised to exponents, we'll be multiplying. Right here, here's how this works. Remember, multiplication, division, they're on the same level. They're not different. They're on the same level. What's one operational level below the multiplication that I see? Addition. It literally works that way. And hopefully that makes sense because we're doing that repeated operation of multiplication from before. So we're just getting to add up how many 5s are being multiplied. It drops an operation every time. If you see multiplication of the same bases, you're going to be adding. Always do one operational level below what you see. It's a good way to remember it. So if I see multiplication, I'm adding. I'm never seeing multiplication and multiplying. It never happens. Let's try some more. This is going to be very quick. I'm going to show you on some weird ones, and I expect you to do about these last 3 by yourself, so when we get there, I'm going to have you do that. So let's look at it. Number 1 thing is identifying whether we're multiplying or not, because the product rule, in order for this to work, in order for us to do one level below what we see, we got to identify what we're seeing. So x to the third, x to the 8th. Anytime you have variables next to each other, you are inherently multiplying. So here's how I'm looking at it. I'm going to model my thinking right now. I'm seeing, hey, I get a product, I get multiplication. I have common bases. Oh, I'm multiplying common bases. What's one level below multiplication? Well, it's addition. I'm going to be adding my exponents. Do I really want to write out x to the third 3 times and x to the eighth 8 times? I don't want to do that. I don't want to have to do that every time, because even if we did, we'd have 3x's, we'd have 8x's. Can you picture it? And then you're just multiplying 3x's together and then another 8x's together and multiplying that. That's 11x's. That's exactly what we're doing. We're just doing it faster. What we do is one level below what we see with exponents. Now, how about the next one? So I'm looking at it. I see a product. I know variables next to each other. I have a product. I'm looking for a common base. It fails. If you don't have common bases, this falls apart. Because you could write out 3x's and 8y's, but there's no way to represent that as one exponent. There's no way to represent that as one base either. So we're done. That's as far as we can go. There's no way to make that a simpler format for us. Now, I'm not saying there's no answer. I mean, that just is the final answer that we get. Most of these things will be accomplished in other problems. How about the next one? What are we doing? Well, I see multiplication here, but check this out. Every time you have a number next to a variable, you're also inherently multiplying. Now, here's what's great about multiplication. So don't let this wig you out. This is not a hard problem. But here's what we can do. With multiplication, which is awesome, you can reassociate it. You can commute it, which means it doesn't matter the order in which you accomplish any of this stuff. So if everything is multiplied together, I could really rewrite this as 3 times 4, and then m to the third times m to the sixth. Do you actually have to rewrite it to do this? No. I'm just showing you it's possible. I'm showing you that because we could reassociate, because we could interchange these two or commute that, I can now multiply my numbers times my numbers. But I'm going to take a pause here for just a second and say that when working with exponent rules, a lot of times people fall back and try to change what they already know. Like when I say, oh, well, I mean, you're multiplying, so you got to add. No, I'm not saying that. What you do with the exponents is one level below what you see operationally. So what you do with these, not the m's, you're not doing anything with the m's, not the 3 times the 4, those aren't exponents. What you do with exponents is one level below what you see. That's why they're called exponent rules, not just rules. We already know how to multiply numbers. We already know that 3 times 4 is 12. But I tell you what, I get a lot of people who put 7 because they fall into that trap of, oh, if I'm multiplying, I got to add. Man, if you're adding every time you multiply, you're going to be really screwed up, all right? What you do with your exponents is one level below. The rest of the stuff, you already know it. So 3 times 4, that's still 12. Now look at this. I have m to the third times m to the sixth. My exponent rules take over for my exponents. Yes, I have common bases. Yes, I'm multiplying. One level below the multiplication is addition, so I'm going to be adding the exponents. I don't add the m's. I'm not getting 2m. I'm still getting m. I'm just adding the exponents. That's why they're called exponent rules. It's one level below what you see. So we get 12 normally. That's just multiplication. And then m to the, let's see, one level below multiplication. I'm seeing multiplication of common bases. I need to do one level below for exponents. I'm adding the exponents. 9th, not 18th. We're not multiplying. And we're not getting 7 here. I need that to make sense. Don't miss that, okay? Because we can reassociate or recommute, we can go directly from here to here. Yes, multiply your numbers times numbers. 3 times 4 is 12. That's cool. Everything's multiplied together. That's what we want. When you get to your exponent rules, when you get to your exponents, that's when the exponent rules take over. That's when we go m to the third, m to the sixth. I know I'm multiplying. I need to do one level below that for my exponents. We're adding. Now, what operation does distribution really do when you think about it? When you do this, what are you doing? Well, you're not adding, you're actually multiplying. So when you see distribution, you're actually seeing multiplication. I need that to make sense because of the way I'm teaching you. What you do is one level below what you see when you deal with exponents. So if we see distribution, we're really multiplying. That's what we're doing. We're seeing multiplication. I hope that makes sense to you. Distribution means multiply. So we're seeing multiplication. What do we do with the exponents? One level below what we see. So if we see multiplication, we should be adding exponents. Now, in order for that to work, I'm going to give you a huge hint, something that helps out a lot of students. If you don't have if a term doesn't have an exponent, give it 1. Like literally, give it 1. So x squared, that's got an exponent. I like that. This term doesn't have an exponent. I'm going to give it 1. Because if it doesn't have an exponent, it's a little hidden 1 up there. It's not 0. Remember, anything to the 0 power is 1. That's not what we have. We have x to the first. Here, 2x to the second, that's fine. So, giant recap. When we're multiplying common bases, we're adding exponents. What you do with exponents is one level below what we see. We can do it with anything that has common bases. Common bases are a necessity. You can't do it without them. If we have multiplication with numbers, don't forget that we can multiply the numbers. What you do with numbers is what you freaking do with numbers. But what we do with exponents is one level below what we see. When we get down to distribution, we are seeing multiplication. So we have x to the second times x to the first. And you could actually write that out. I wouldn't require you to do that. But you are literally doing that. You're seeing multiplication. What do you do with the exponents? You're adding. That would be x to the third. We would be adding our exponents. Now, how about, so this is where we get in the x to the third. When we're seeing distribution, we're seeing multiplication. How about x times 2x to the second? X squared times 2x to the second. Because that's what distribution means. If distribution means multiplication, we're seeing multiplication. One level below that is addition. That's what we do with exponents. 2 plus 1, that's why we write the 1. Do you see it? So that we don't miss it, so we don't accidentally forget. Because a lot of people give me a 2 here because they're just not seeing the 1. Write a 1 for anything that doesn't have an exponent. So 2 plus 1, that's our 3. X squared times 2x squared, well, our numbers times our numbers give us 2. 1x squared times 2x squared. 1 times 2 is 2. X to the, man, I should change that 2 to a 3 so you really see what's going on. But to the 4th power. Not because 2 times 2 is 4, because 2 plus 2 is 4. What we do is one level below what we see. If we're seeing distribution, you're seeing multiplication. Add your exponents. Multiply your numbers. Add your exponents. Now, there's a whole lot of people who, when I ask them, go, and I ask them, how can you continue? They go, yeah, give me a negative 2x. Or negative 2x to negative 1. Woo! Negative exponents, for real? Yeah, but that's way later. You can't combine them. And I'll talk right now about why. I'm gonna give it away about like terms and what like terms mean right now. I've been talking about the last 20 minutes about what you do with exponents is one level operationally below what you see. If you see multiplication of common bases, you are adding exponents. When we see division, we'll be subtracting exponents. Now, remember that exponent rules only have to do with exponents. They're what you do with the exponents. If you see multiplication, you add the exponents. They're exponent rules. What if you see addition or subtraction? What do you do with the exponents? Well, let's look. What's below addition? Not subtraction. These are same level. What's below addition? Nothing. What's below subtraction? Nothing. There's no way to change your exponents. You can't do anything with them. So what's the only way in the world, and I'm really asking you, I need you to think about it. What's the only way in the world that you'd be able to add or subtract and not change the exponent? Because remember, if you're adding or subtracting, there's nothing below that. You can't change it. So what's the only thing in the world that you could do and not change the exponent? How could you combine terms with addition or subtraction and not change the exponent? Well, those exponents would have to be identical. If that were a 4, you could combine those and not have to change the exponent. What you do with exponents is one level below what you see. If you see multiplication, you're adding. If you see division, you're subtracting. If you see addition or subtraction, you're nothinging. You can't do anything. So they'd have to be identical for you to not get to do anything with the exponents. You certainly can't add them, can you? Because if you added them, you'd be saying you're multiplying. If you subtract them, you'd be saying you're dividing. We're not doing either. So in order for these to be added or subtracted, you'd have to have the same exact exponent. If not, you're breaking some rules. We cannot go any further than that because in order to combine those, you change your exponent. What are you going to put, 34? Or 4 or 3 or 1? You'd have to change your exponent somehow. So because we're adding subtracting, there's nothing below that. We can't change exponents when adding subtracting. Can't change them. They're exponent rules. You can't do it. So we wouldn't be able to go any further. There's nothing to do here. Interesting. What I'd like is to do one more. I'm gonna have you do these 3 if you can. That one's a weird one. You can think about it though. But I do want to talk about this one first. What do you have if you don't have an exponent? So if I say do exponent rules and you have a factor without an exponent, you can always give it 1. That's fine. Just remember that it's not 0. So when you're doing this, am I multiplying? Yeah. I got some common bases. Great. What do I do when I have multiplication of common bases? With the exponents, one level below multiplication is addition. So I'm seeing multiplication. That means we're adding exponents. You can probably see that a lot of people give me y to the 5th if they're going to make a mistake because they, in their head, they go so fast. They go, oh, 5 times 1 is 5. Yeah, you're right. But when we see multiplication, we should be going one level below. We should be going one operation level below. We should be adding. That's y to the 6th. Take a moment and try those 3. Remember, numbers times numbers are fine. They're not exponents. Exponent rules can't affect them. But deal with these things. Remember, we're seeing multiplication. The exponent rules say what we do with exponents is one operation level below. You're seeing multiplication here because we have distribution. And then work on that one if you can. Now, I'm going to get to it right now. So I know that everything here is multiplied together. Because of that, this allows me to multiply numbers times numbers. 4 and 9 are not exponents, folks. Exponent rules can't affect them. You're just multiplying. Exponent rules do affect common bases being multiplied together. What I do with the exponents is one operation level below what I see. So 4 times 9, that's just 4 times 9, 36. X to the 2nd times x to the 7th is x to the, I'm seeing multiplication, I'm going to add the exponents, x to the 9th. Next one, if I see distribution, distribution is a multiplication concept. We're seeing multiplication. So I'm going to look through here. That's got an exponent, looks real good. This one, I'm going to give it 1 so I don't miscount. This is 2. Okay, that's fine. If I see distribution, I'm seeing multiplication. So off to the side, I can write x to the 3rd times 2x to the 1st if I need to. If that's you, that's fine. Don't worry about doing that. If I don't, then I go, okay, 1 times 2 is 2. X to the 3rd times x to the 2nd. What I do with the exponents is one level below what I see. I'm seeing multiplication. I'll be adding the exponents. That either way gives you 2x to the 4th. Next, I see x to the 3rd times 3x squared by distribution. So I know, well, let's see, I got a plus here. 1 times 3 gives us 3. X to the 3rd times x to the 2nd. Okay, now I have common bases. Now I'm in the category of exponent rules. What I do with the exponents is one level below what I see. If I'm seeing multiplication, I see distribution, that is multiplication, I'm going to be adding the exponents. Multiplying the numbers, adding the exponents. No. Yes, that's what I want. I want exponent rules to be flawless. Firstly, don't confuse our numbers. You're still multiplying numbers times numbers. Those aren't exponents, hence exponent rules can't affect them. But anytime we multiply common bases, what we do with the exponents is one level below what we see. We're going to add those exponents. Now, can you keep going? I know some people really want to give me, 5x to the 9th or something? Can we do it? Well, let's see. What are we doing to combine those? Well, you're adding. What's below addition operationally? Nothing. So in order to, and that'd be what you do with your exponents, okay? What we would do with our exponents when adding terms. When adding, what you do with exponents would be nothing. How do you do nothing to your exponents? You keep them the same. That means that they'd have to be the same to start with so that you could add them and they not change. That's why we don't get to combine terms that don't have the same exponent. There's nothing to do with the exponents. You can't change them. You certainly can't add them. Imagine that if you added those, if you got x to the 9th, you'd be telling me that you'd be multiplying, because x to the 4th times x to the 5th is x to the 9th. You're not multiplying. So when we try to do this and you give me x to the 9th, you're telling me you're multiplying when you're actually adding. You can't do it. Last one, kind of a weird one. It stems from this idea, actually, it's the same thing. When you multiply common bases, exactly the same thing together, we're really just adding our exponents. Well, these are the same thing, and in fact, they are multiplied together, parentheses times parentheses. This has an exponent of 3. Oh, that doesn't have an exponent. Give it one. Literally. Well, if we're multiplying common bases, you're noticing right from the very beginning that really you don't change your base ever. The exponent takes care of that multiplication for you. So we don't change our y, we don't change our x minus y. That is our base. It's a weird one, but that's our base. We have common bases multiplied together. What I do with exponents is one operational level below what I see. So what I'm doing with my exponents is one level below multiplication. Adding them, let's see, 1 plus 3, that's 4. One last thing, one of the best pieces of advice I can give you is don't make up your own math. I'm begging you, don't make up your own math. What I mean is, don't take this and go, well, obviously this is x to the 4th minus y to the 4th, hello, because, I mean, that's a little 1, that's a little 1, so you distribute it. I mean, you heard this before. That's a no-no. Here's why. What you can do, listen carefully, what you can do with exponents is also one operational level below exponent, what you have, which means that in order to distribute exponents, you have to have one level below. You have to have multiplication. In order to distribute something, you have one level below what you're distributing. So in order to distribute exponents, you have to have multiplication or division. You can't distribute exponents across 2 levels below. You cannot distribute exponents across addition subtraction. It's impossible. So can you distribute exponents? Yes, one level below what you see. It's always one level below. I hope that makes sense. You don't get to do this. You can't distribute exponents across addition subtraction. You can distribute multiplication across addition. Oh my gosh, it makes sense. You can distribute multiplication one level below. So what you distribute has to be one level below what you see. If you see multiplication, yeah, you can distribute that across addition and subtraction. If you see exponents, no, you can't distribute across addition and subtraction. Across multiplication, division, yes. We get to that in the next video. We'll talk about that. But don't make this mistake. How exponent rules work, how distribution works, is one level below, one operational level below what you see. Keep that with you and it will serve you very well. This is a no-no. I'll see you next time.